Welcome back to my calculus lessons. Today we are going to learn about derivatives, the next thing you learn in calculus. Derivatives are basically, how would I put it? You know how you can find the slope of a graph of, like y equals mx plus b and stuff you can find the slope of a line if you know 2 points, and you can find the change in x by the change in y. The slope is equal to exactly that. And I'm sure, like, in elementary school, middle school, before you even go into calculus, basically you can't find the slope on a curve because that's just forbidden, That's like cursed stuff, because a curve, it doesn't have a slope, it's curve. It's a curve. Derivatives say fuck you, and they do that anyway. And that is great because it made me understand math more easily, because surely you can define, like, if you zoom in close enough to like a curve, you can eventually like see it just flatten out until it just turns into a, sort of like that. I never understood why we couldn't do that in class, because, I don't know, I'm a nerd. But derivatives basically allow you to do that. Find the slope at a single point, basically. Because, like, given any graph with a curve, or I guess we can use a different one, or I don't know, maybe something like this might be good. A graph like that, you can basically find the slope at a single point on this graph, basically. Now, if we were to try and find like without trying to go into like the mathy stuff just yet, just the conceptual understanding, what do you guys think the derivative at this point is? What's the slope at this specific point? Basically, I don't know, maybe you guys imagine some sort of line that's sort of just only touching that point, just goes straight on and upwards, that's the derivative. And yeah, that's kind of it, basically. There isn't much to it when it comes to, at the moment anyway, when it comes to derivatives at this level. So we can basically define derivatives as like the rate of change or slope of a function of any function at a point, which must sort of defy logic somehow, because because of how the slope is defined, it's basically the change in y over the change in x. If you're looking at just a single point, though, there is no change in y or x because it's just one point. If you were to try like to find, say 1, 1 on like any random curve, I guess, and then try and do that, like we're trying to find the change in x and change in y between the same point, it's just going to be equal to 0 over 0, and that's indefinite. Or rather, no, not indefinite, undefined. No, wait. What was the word again? Indeterminate. And that must seem extremely strange, but if you guys know about limits, from the last lesson, maybe you guys can see where we're going with this, but if not, you must be wondering, how do we find the change in y and change in x for on a single point? Because if we just try and find the change between, if you're trying to find, if like, look, if you try to like find the change of a single point from another point, but that's, you know, I'm great at explaining things, you guys can probably freaking tell, but suppose we have a point, and, you know, we're trying to find some, whatever it is, you know, we're trying to find like the slope between 2 points, right? But like, if these points are the exact same thing, then there is no change. Change of x equals 0 and change of y equals 0. They're both the same point if, you know. Of course, this isn't really, just imagine like both of them just sort of fuse together or something, you know, like they just come closer and closer together until they are exactly the same point, yeah? I think that must have been, I feel like that was extremely not subtle at all, but yeah, that's basically the idea. For those who didn't get it, basically the entire thing that I'm trying to say is that in order to find like the derivative of a function, or a derivative at a certain point, say c, I guess. It could be 10 or 69, doesn't really matter, but that's what the variable's for. Hope you guys passed algebra and understand that, but yeah. Letters just represent the frickin' thing. And this can also be any number, but it doesn't really matter, but so I'm going to apply 2 points here, right? And we're going to say that this is like c plus h. H can be some arbitrary number, any number. It could be, c could be 10, this could be 10 plus 5, 10 plus 1, 10 plus 0.5. And that was also extremely not subtle at all. We can say that the slope, or, you know, the line between these 2 points is, I believe it's called a secant, I believe. The line between 2 points on a curve, you know, sort of like this, is, I believe it's called secant. I didn't refresh my knowledge on that, but that's what it's called. But basically, the change in x here, assuming this is like the x and y axis and stuff, this is basically h. And right around here, I guess we can also define this real quickly. So this is basically f of x at c, so f of c, and this is f of c plus h. And that's the change in y. But it doesn't necessarily mean that change of y is equal to like h2. That's not how it works. But if you guys are starting to get the picture now, how do we, I want to ask again, how do we find the slope of, you know, a graph, a curve at a single point, if, you know, you need 2 points at least to find the slope? The limit is basically the helpful thing here, because basically if h equals 0, then, you know, both of these are the exact same number, and, you know, as if h is 0, then f of c is also equal to f of c, and, you know, they're both the same point if h up, is 0, right? But we can't really just say h is 0, otherwise we just fall into the same problem, so we just make it approach 0, which is the fun thing about limits. And I'm pretty sure those are the only things limits are useful for in class, not gonna lie, because they're only useful for helping you understand what derivatives are, and also some other things like divergence and convergence, but we won't get into that until like very later. But basically, we're basically finding the slope between these 2 points, and the change of y and change of x. It's basically, if we had to define it, we're trying to find the slope as h approaches 0. So we're trying to find like f of c plus h. Fuck, my camera dropped. C plus h minus f of c. That's the slope between these 2 points. If h wasn't 0 and it was like some number. So like if c plus h was like 15, then the slope here would be like 5, and the change would also be, or rather, the h would be 5, but the y, depending on the function, if it were like x squared, then like the slope, the change would be different. I'm not going to calculate that because it's not really important. And of course, the change of x is basically the right here, c plus h minus c. And of course, that can be simplified because these cancel out, and we have the limit as h approaches 0. That was a horribly written limit. Of x, c plus h minus f of c over h. Now, I'm guessing you guys can see a problem. If you just plug in 0 into this, it just ends up with something divided by 0. We'll just call this like x because I don't know, we're not using x at the moment. So basically we just ended up with a huge problem there. But of course there is something that I feel like I don't know how else to I don't know how to really describe it other than like try and apply it onto an actual function. Because like let's try and find a derivative of like, I don't know. Rather than we define the limit as h approaches 0 of f of c plus h minus f of c, we replace that c with like x, so that way we sort of define a function of some sort. The x's would cancel down there, so it doesn't really matter. Let's try and make it continuous because I don't know how to explain it for like an individual point. But basically, let me just color this in real quick so that way it looks pretty when I make the thumbnail. If we were to try to say like f of x equals like x squared or something like that, let's define a simple little function here. Red lines. Sorry about the cut there. Blech. Sorry about the cut there. Some dumbass decided to walk in on me. That was my father. But basically, if I were to try and apply like the limit on this function here, without like really thinking about it, I guess, just say the limit of h over 0 is equal to like x plus h squared minus x squared over h. we just apply 0 in directly, we just get x squared minus x squared over 0, and this is equal to 0 over 0. And it wouldn't make any sense, right? So there is something that you probably would have noticed. I mean, I guess, I don't know how else to put it, but maybe instead of just plugging h right in, maybe we make it a bit more complicated and expand it. The limit of h approaches 0 of x plus h squared minus x squared is over h. We'll end up with that if we just plug it in. So how about we expand this part right here and turn it into like limit of h approaches 0. We basically end up with x squared plus 2x. No, let me just do this real quickly in my head. We got xh plus h squared minus x squared over h. Yeah, I was right the first time. I just confused myself a little bit because I had a little brain fart. And I'm guessing you guys can sort of see what's going to happen now, because fun right here. We get rid of this, we get rid of this, we get rid of one of these. These two terms cancel, so then we just end up with like what's a good color to use? Screw it, purple again. The limit of h approaches 0 is basically equal to, or rather, I mean, like, the limit as h approaches 0, it simplifies to 2x. Just 2x. All the h's are gone. So, it's just equal to 2x. There's no, as h approaches 0, there's no h in the problem at all, so it just ends up as 2x. And that's the slope of x squared, the derivative of x squared. Now, we could basically place c in for x at this point because, that's how it works for any given number and stuff. So, like, for like the function x squared at 2, the slope is 4. The derivative of f at 2 is basically 4. Of course, that also happens to be what the y value at that point equals, but like for 3, the slope would be 6 and the value would be like 9 and stuff. But yeah, it really is kinda that simple. I don't know how, I mean, it probably is a bit complicated for new people really getting into this, but it's kind of just that simple. The derivative is just basically the slope at a given point, and we use limits to sort of get there. We basically sort of cheated because we actually did use 2 points, but we just made like these 2 points on whatever curve that happened to, whatever curve it was. We basically just made them approach each other so closely that it doesn't matter what those 2 points, we just made those 2 points the same point. We just made them approach each other, even though they're technically 2 separate points. It doesn't actually reach, the point that we want to define the derivative as. That's basically how It works. Yeah, it's basically the derivative for you. We basically use limits to cheat the system and say that, we can define it at 1 point. We just need to use 2 points. Makes sense, right? That does. I don't think this update to this 2D thing made my model. I think my model's less expressive now. Da. Well, it checked my eyes properly instead of doing those derpy little things, but But that was a bit of a tangent there, I digress. Now, basically, now that you know that, well, actually, before I go on, basically the limit of f of x plus h minus f of x over h. That's the formal definition of a derivative. Basically, given any f of x, you should be able to apply to this and output a derivative. And we have a little special notation for derivatives, or multiple notations. This is f prime. This is basically how we notate like derivatives, and there's also d of dx. That's also another way to denote it. And I think there was also f dot, which I don't know what the actual thing was actually called. F dot is basically what I remember it being called. I don't think it's actually called that, but call it f dot. But we probably won't be using that notation anytime soon at all. I've mainly only used these notations throughout my high school and college stuff. And basically, what it would look like in, on a sheet of paper and stuff, like f prime of x is equal to like 2x, and f of x is equal to like x squared. And also like df dx is equal to 2x if f is equal to f of x is equal to x squared. That's how it might look like. There's also like d dx of x squared equals 2x. That's like another way to really notate things. And let me just sort of recolor all these. That way they're a bit more separate, a bit more less dull. But basically, yeah. You can basically do like this and stuff, d of dx or f prime of x. And f dot, I don't remember how to use that, not gonna lie. So yeah. But that's basically the simplification of the derivative for you, the basic concept of it. But given any function, you should be able to find the derivative of it. And I'm just going to list a whole bunch without really proving them. You guys can do the exercise yourselves, or you do something else or something to try and figure out the derivative yourself. But basically, I'm going to list a whole bunch of derivative memory stuff. You can search it up on Google, like a huge derivative list and stuff that will be helpful. But basically, here are all the derivatives that people have found. First off, x squared is equal to 2, or the derivative of x squared does not equal 2x. Please do not think that. The derivative of dx of x3 is equal to 3x squared. And the derivative of x tetrasect or something is basically 4x cubed. And you guys may have noticed connection. The rule is basically the derivative of x to the n power is equal to nx n minus 1, where n is whatever power that you were initially raising it to, raising x to. Another thing I've also found, the derivative of functions like sine of x is basically equal to cosine of x. The derivative of cosine of x is not exactly sine of x, it's the negative of sine of x. And it sort of just goes back. Negative sine of x equals negative cosine of x, and negative cosine of x brings you back to sine of x. It's just a huge loop when it comes to these things. You can look at the graph of like sine of x, cosine of x, negative sine of x, and negative cosine of x, and you'll notice that well, I guess it's a bit too advanced. I think I forgot a step when I tried to introduce this, but I'll cover this real soon when I cover the rest of the derivatives. The derivative of natural log of x is 1 over x. Another derivative, e of x, is basically itself. And I guess that's all the useful stuff that you probably need to know, but like basically there's like a huge list of stuff that you can just look up, a huge derivative list that you should probably memorize. Of course, eventually, like in class, the teacher should go through bit by bit, like how on earth each of these are derivative of, like why these are the derivatives and stuff. But before I do go ahead of myself, basically, you may have noticed that x squared, right? Defining whatever x squared here, that's a function, and its derivative to x is also a function in of itself. And I guess that's I feel like that might be interesting for you guys to know, but like that's basically another way of how people may be able to find derivatives. But yeah, I also probably introduced this again real too quick. Basically, the derivatives themselves can also have derivatives, because the derivatives themselves, if you had like the graph defined and stuff, you can basically do a little thing with them again. So like dx of x squared is equal to 2x. And well, let's say that, let's just define f of x to be x squared again. I'm pretty sure that's obvious, but let's just do this again. But that's basically the notation in this form of like a double derivative. The other one is basically f double prime. This is basically equal to 2. These technically have parentheses, but mathematicians are lazy as fuck, so that's why they aren't really that thing. But yeah, And I should probably explain where the dx thing comes from. As the limit sort of approach of, you know, all that stuff approaches, you know, as h approaches 0, a change in x and change in y sort of, you know, become 0 and stuff, and, you know, they kind of just become different, I guess. I don't know why. I kind of forgot the reasoning got lost to me, but basically the dx dy dx thing is basically for, they're called, what were they called again? Well, I completely forgot, but basically, no, I swear I can remember it, but I guess I'll just continue on before it gets too boring. But it's basically used for like infinitesimally small things. The dx and stuff, they're basically supposed to mean like extremely small values and stuff. And I guess, how on earth would I put it? The derivative dx and dy are like approximations, basically, because we're using limits to sort of get closer and closer and stuff. These are approximations. But like dx and dy, they are basically the actual change of a thing, of the function. So like exact change, I guess. That's basically the difference. Although they're sort of similar, the nuance and stuff, basically these are different because, you know, you'll probably get completely different values. Dy doesn't necessarily mean change in y, and dx doesn't necessarily mean change in x, but, you know, in class you might have been introduced to this stuff in that kind of way, where like dx is basically change in x, but also not really. It's close, but not the same. And I'm gonna need to refresh myself a little bit more regarding derivatives if I want to sort of explain more about what the dx, dy, and, you know, how to really manipulate them and stuff to do all sorts of stuff. But let's ignore all that stuff for the time being, because now I'm gonna actually show you like how to do more stuff with it, which is great because I'm a terrible teacher, but yeah, whatever. Basically, given any, I'm guessing, you know, given any function x, you should be able to find the derivative of it. You know, because in order to like just plug it back into the limit of h over 0 and all that jazz. Mathematicians found that extremely tedious, tiring, and stupid as all hell, so they made that list I made earlier, right here, as a way to just refer back to. This is the whole list that you'll remember and sort of memorize. You know, just drop it back in, because there's a few rules of derivatives that make it easy for us to just not give a damn about all that stuff. Basically, there are a few rules of derivatives that basically are the same as regular math. Suppose you have two functions, f of x and g of x. If you were to find the derivative of f of x plus g of x, what's the derivative of that? Because, like, I guess you guys can sort of think, you know, f of x plus g of x, let's say f of x plus g of x is basically like x plus x squared or something like that. Whichever one, it doesn't really matter, but I believe that would be x plus 1. So then something like that, where the intersection is, where that's the negative 1 is the intersection at 0. The derivative then the derivative of this combined function basically of f of x plus g of x, it's not necessarily x squared, even though it's sort of shifted by 1. But basically, basically the derivative of two functions added together is just the derivative of that function plus the derivative of that function, which makes it easy to do. It doesn't really, you don't need any like complex thing to plug back in. So like you had like, for example, sine of x plus x cubed, and we're trying to find the derivative of that. You would just end up with cosine x plus 3x squared. You don't need to know why those are. You could just straight up memorize them. Feel free to cheat on that, though. You know? But yeah, that's basically the derivative. And, oh yeah, other things I should probably add on to this list, I suppose. The derivative of a constant of any number, like 1, 2, just the number itself, it just equals 0. Because, you know, the actual graph is just a straight line. There's no slope. It's just 0. So, yeah. And there are a few other rules of derivatives, but like for addition and subtraction, if if instead you had f of x minus g of x and stuff, it's basically the same thing. You just find the derivative of these and just like subtract them. So if it was like something like ex minus cosine of x, then we get like e of x, e of x plus sine of x, basically. Of course, this is technically minus sine of x, but you know, I just simplified it because I just did that in my head. Probably should have went it more slowly, but that's why I'm not a good teacher. And this is why I shouldn't be teaching this, but, you know. And it also here's like a little connection to multivariable calculus that I want to plug in right now, because this is basically the intent of my series. So sort of get you introduced to calculus and eventually move you up to multivariable. But like, if you had to find, or rather, I guess I'm getting a little bit ahead of myself, but if you were to find like the derivative of dx of like some function x plus like the derivative of some function that has y as a variable, you basically just get, this. It's sort of similar to that I sort of noticed when I first learned multivariable calculus, but if you were to like sort of the right, you find the derivative of functions to different variables, they still sort of just do that. In a multivariable class, I'm not introducing you to multivariable functions yet, just like the thing. You don't really need to understand it. You just need to look at how the letters cancel, basically. But if you were to find like the derivative of x to like a function y, if y is a variable in of itself, and like multivariable functions usually look like some other variable where it's defined by two different variables, or it could be like or a variable can be, or a multivariable function can be defined by one term, but basically we're just sort of thinking about it like that, where basically these are the inputs. This is our f of x, y equals z. We usually treat like another variable which we don't really care about as like a constant. So I guess as an example, we have 2x plus 3xy plus y squared. If we were to find this with respect to x, I'm guessing it should be easy to find the derivative of that and stuff. It's just 2. But this might be a bit more complicated, and this, you probably don't even know what to do with this. But basically, we treat that other variable as a constant because we're finding the change in x as x changes. But the other variables stay the same. We're not changing y here. So these are no different than constants. So you could think of it as instead as 3y. This is the constant x, and this is just y squared. It's just a constant. Doesn't really matter. So we get 2 plus 3y because, x doesn't have a power. It just cancels out. That's the slope right here. And since this is just a constant, just 0, there's no change in, the slope doesn't change for this function as x changes. It's fine as y here. Though it's also different in multivariable calculus, I guess, in that I believe you have to use like a partial notation. I forget, but that's a bit of the nuance there. And as a challenge, I guess, if you guys sort of understand what I'm talking about with regards to multiple variables and treating the other variable as a constant, not as a variable, not as something that changes, not as something that really matters, can you do the same thing? Find the derivative of that same function, but this time with respect to y. If you guys sort of understand what I mean, but you should be able to find the answer. But let me explain it, just to give you a little introduction to how derivatives work in multivariable functions, which we will eventually get there. We will get there. I plan for everyone to learn how to do that and that kind of thing. But remember, we're trying to find the change in y. We're trying to find like the slope and stuff, the change with respect to y, as y changes. Meaning that this variable here does not change. So this is an entire constant. This part is a constant. And these parts right here, this is the variable that changes. This is the function, this is the variable that changes. And so this is basically 0. Well, I should probably add that too. Plus 3x plus 2y. If you guys understood that. That's sort of their little introduction, to multivariable calculus and the derivatives using multivariables. So another way to sort of connect it, I guess, or to sort of bring it back and also sort of expand on that a little bit, I guess. the first rule regarding the derivatives is that the derivative of functions plus a function plus a function plus whatever is basically equal to f prime, the derivative of the first function plus the derivative of the second function. Doesn't really matter how you notate it. I don't know how to notate that, but you get the point basically. And it also applies in the same way to multivariable functions of x, y, z, w, etc. Derivative with respect to like one variable, you sort of just focus on that one variable and treat the other variables as a constant. So like 6 is basically, you can sort of think of it like that, where z is 2, z equals 2 at the point where we're trying to evaluate the multivariable derivative at, which probably sounds confusing as hell because you haven't been introduced to that yet, but stick with me for a little bit longer as I ramble about stuff that you probably don't and shouldn't be really learning at this moment. But multivariable functions, given any function x plus 2y, 2xy plus 3y z plus 5 xz and plus y squared plus z cubed. If you were to try to find the derivative with respect to one of these variables, dx or the derivative of dy or dz, again, you treat the other variables like if you're trying to evaluate for x here, right here. Let me change the color of some of these so that way it's a bit more easier for me to get through and explain in some sort of way. Let's make this a bit brighter pink. But if you're doing it with respect to x, you treat the y and z variables as constants. If you were evaluating it with like y, you treat the other variables as constants. And if you're doing it with z, again, this is also a constant. All of these are this is entire d thing is a constant. That's a constant. That's a constant. And this is a constant. And you evaluate it as if these are just like, like for this, it's basically, you could think of it as like 3y is like no different than like 6z or, that kind of thing. The coefficient, that's what the number before like a variable is. That's the coefficient, and like treat it as like a regular coefficient. You don't care about the variable. Like the y can be literally any number. It could be 2, 5, doesn't matter. This is a constant. It doesn't change. Only z changes, and that's how and we define the slope as the rate of change of something, as a variable changes. So as z changes, the number increases or decreases because of the slope at that point. And of course, since we're not checking whether or not y is changing or not, that we just ignore it entirely. We just don't treat it as a variable. We treat it as a constant. We treat it as no different than a regular number, nothing else. And it applies to multivariables in that sort of way because, you could just evaluate them differently. You can sort of treat them as if they're just, yeah. I don't know how else to explain it though, but yeah, that's a little glimpse into multivariable calculus. You basically do the same thing you have been in regular calculus, but with more variables, more letters, maybe even some Greek letters later. Yay! So once you've basically mastered like how to deal with derivatives, then you can sort of figure out how to deal with like derivatives with multiple variables. And to end this off, I'm going to finish this off by like, actually writing the rest of the derivative rules. So you know that, the derivative of like f of x plus g of x is equal to the derivative of x plus the derivative of g. But say you have f of x times g of x and f of x divided by g of x, which is basically the same thing, except like, it's just, you're basically multiplying by like the inverse of g of x, basically, but, And there's also f of g of x. The derivative of a function f of x times g of x is equal to f of x times the derivative of g plus the derivative of f times g of x. And the same also is similar to this, except, because it's a bit inversed and stuff, it's basically the same thing. F of x, g of x minus f prime of x and g of x over g of x squared. Or you could sort of notate it like that. And for the chain rule, basically you go g prime of x times f prime of g of x. And I'll show you an example of all of them. So let's say x cubed of cosine x. We're trying to find the derivative of that. Let me give it a little more space so that I'm going to actually write that. D of that over derivative d of x is basically equal to 3x squared, or rather x cubed. We're going to say that this is our f of x and this is our g of x. Doesn't really matter which order it is, but let's just say it is. I'm just defining it as is. You could do it the opposite way. In fact, why don't we do that then? And this is basically negative sine of x. That's the derivative of g, and then we add 3x cubed cosine of x. That's basically the derivative of that huge thing. The reverse, if we just switch them around, is basically 3x squared cosine x minus x cubed sine of x. Next function we will analyze is the derivative of I guess ex over I guess 2x. That is basically equal to, let's say again that this is our f of x. That's what it's equal to, and this is our g of x. We will then do the little wild thing. We can do the bottom one first. This is basically 4x squared, because it's less convoluted, because take a look at all this crap. but ex2 2ex, and we do minus, we don't change f of x, we find the derivative of g of x and then multiply it to like f of x, and then we do the opposite for the second side. The derivative of ex is just ex itself, so yay. And then we end up with that. And we can also simplify it down a little bit because, rather, I guess not. It's basically 2ex 1 minus x over 4x squared. You can't simplify that down, but yeah. And I guess another thing would be, the final thing I guess we should look at is for the chain rule. Let's do sine of x tetrasect, I guess. And there's no real short way to say it. X to the 4th power. Tetrasect is like the word for like the 4D cubed and stuff, right? I don't know, but you know what I mean. And this is our f here, and this is g of x there. This is all not that hard, but we find the derivative of that for x that, and then we find the derivative of f, which is cosine, but we don't change what's inside, so that's basically it. That's how you solve. That's sort of how you go through them, I guess. So basically, you sort of just combine like the functions and their derivatives together when they're like multiplied, divided, and are in each other. The chain rule is also used to find another derivative that we know about. E of x. What about some constant a to the x power? Basically, we don't. That the derivative of e of x when it's just e of x, but we don't know what that is. But we can figure it out because we know about the chain rule now. A of x is basically equal to e ln of a x. Or we could just say x ln of a. That's sort of how I usually notate it. And this is a constant. It's not a function. A could be, this entire thing could be ln of 2 ln of e, which is just equal to 1. Or the entire thing could just be equal to pi, doesn't really matter. But the derivative of ax is basically ln a ex, because that's sort of or ln of a ax, that's what I mean. Because you're basically using the chain rule there. Basically, it's basically, the derivative of x to the ln a is ln a, and that's what we put out here. And we don't change what's inside this function, we just find the derivative of it, which is basically ex, and that you don't change it. That's basically another derivative for you. And again, it also connects to like multiple variables as well for multivariable calculus, which I am a bit too tired of. I do not feel like going through that, but I'm guessing you guys can probably figure it out for yourselves, because like given any function that you want to sort of go through, I don't know, 2xy squared sine of xy. Let's say that cursed equation there, and you want to find the derivative with respect to I don't know, let's find the derivative with respect to, like, let's just do both. With respect to both x and y, if this is the quotient rule in multivariable calculus and multivariable derivatives. Again, since we're doing this with x, we treat this little thing as a little constant. So you can think of it as basically 2y. This is basically equal to 2y squared. Or I guess, since we're going to treat both of these as functions that we want to, it doesn't matter which one's f of x or f of y, or g of x, or g of y, whatever, but for basically it's equal to 2xy squared. Derivative of this is basically y sine of x, so this can just be a cube. We can simplify that, and since it's sine, we change that into a cosine of xy minus or plus, basically, since we're treating this as a constant, we have 2y squared sine of xy. That's a multivariable derivative of that, and with respect to y, we treat the x as a constant and the y as a variable. Again, we will be treating both of these as their own functions, and this is basically equal to like 4xy, because the power rule, you basically bring this down, multiply the thing down by the power, and then just subtract 1 from the power, and you get this. 4xy sine of xy plus 2xy squared cosine, well, since there's an extra x that gets out, it's basically 2x squared y squared cosine y of x. And that's the multivariable product rule. And quotients and stuff is basically also the exact same and stuff, but ta-da! This is how much we got through this absolute cursed mess that is calculus. That is derivatives. I covered as much as I could about derivatives and just the conceptual parts. We can work through, I think I should make another video working through problems I can make up on the spot and stuff. But generally, I guess, before I end this video for reals and make a thumbnail real quick, is basically, so long as you have like a list of derivatives that you get in class or something, like a sheet of derivatives, so that way you don't have to memorize all of them to simplify it down, where d and dx of like xn is equal to, you know, nxn plus 1 or minus 1, and you know, so on and so on. And if you know the rules of, you know, of how these interact, I'm excluding the in parentheses x because, you know, they're representing functions. But if you know the rules and the list of derivatives, then practically you should be able to solve most problems given to you. And that's all you really need to know to get through class. The rules and how to really apply them in just a list just conveniently handed for you. Or just use your brain and memorize the entire thing like I did when I was in high school. But yeah, that's derivatives for you. Doesn't take much to solve. It's a rather simple concept, which is kind of convoluted and a pain in the ass to solve at certain points in time, but yeah. And I also feel like I've rushed it a bit, so I'm gonna have to make a video. Another video regarding practice problems is absolutely necessary just for me to get through a point. I rush things way too quickly, so yeah. I'll be giving you guys that video to help you guys work through actual problems instead of just dropping all this on you and expecting you guys to just go through that no problem. But yeah, thank you all so much for watching. Hope you guys learned something important, and I'll see you all in the next video. I have a coffee that nobody donates to and the fan box that nobody also donates to. Please do that. College, that is, the grace period is ending. I have literally no money, no jobs are fucking hiring for some goddamn reason. And yay! COVID's fun. Lockdown's fun. And again, hope you all have a good day though. Please donate if you guys want to see more stuff. I probably will still make more, but probably won't make it much more longer if shit goes down the road, whether I want it to end or not. So yeah. And yeah, I'm gonna go and play some games now. Not gonna lie, I've applied for so many jobs and none of them are responding. I give up and all that. Fuck me.